This is a brief tutorial on trebuchet design, physics, and tuning. Hopefully this will improve your understanding of trebuchets and give you new tricks to improve the distance of your throws. Not sure if this tutorial is worth your time? Here is a simple question that will greatly influence the efficiency of your throw. Here is a motion capture of the arm and counterweight at various points of the throw. Where does the counterweight have the least energy? A, B, or C? Don't know the answer? Unsure why this is relevant to trebuchet design? Then this video could help you throw farther. We should start with the simple question of what is a trebuchet. A trebuchet at its simplest is a device that takes potential energy stored in a counterweight and transfers it to a projectile, ideally as much energy as possible. This can be accomplished by making sure that the projectile is released when everything but the projectile is moving as slowly as possible, the heavy stuff is as low as possible, and the projectile is moving as fast as possible. If you're starting out, it's not entirely clear-cut. One easy solution is to maximize the starting energy. You can do this by having a large counterweight mass or fall distance. However, this tutorial will focus on the efficient transfer of energy from the counterweight to the projectile. This can be accomplished by several simple energy transfer mechanisms. The first mechanism is the lever. If we only rely on this mechanism and place the counterweight and projectile on opposite sides, and have the projectile side of the arm 4 times longer than the counterweight side of the arm, then the projectile must travel 4 times faster than the counterweight at any given time. This fixed ratio of movement is actually used in most trebuchets. This is why you need a well-implemented sling. It's easy to assume that a sling is just a convenient release mechanism. In reality, it plays a major role in energy transfer and can determine whether or not you have an efficient trebuchet. Just watch this example. Note how much faster the projectile is than the tip of the arm. In fact, at a key point, the arm actually goes almost stationary, while the projectile is moving very, very fast. This is called a sling stall point. Here, almost all of the energy is in the projectile, making it a very good place to release. Given the effectiveness of this mechanism, it's not surprising that it has popped up at several points in human history. Unfortunately, having the counterweight fixed directly to the arm doesn't work well. In this configuration, the counterweight makes a major contribution to moment of inertia, and it is very likely that the counterweight will be still moving at the release point. Since the counterweight is the heaviest thing on the device, it's not good for it to move, as it will have a lot of kinetic energy. At the very least, we want the counterweight to sort of move straight up and down. The medieval solution to this problem is the hanging counterweight trebuchet. As the name suggests, they hang the counterweight some distance below the arm. Here's a clip showing how effective this is. This can be hard to see, so I'll plot the motion of the counterweight and the arm for you. As you can see, the counterweight travels almost vertically until its lowest point. It then makes a drastic change in direction and travels horizontally. When the counterweight makes a drastic change in direction, it almost stops, transferring almost all of its energy to the arm and the projectile. This is the counterweight arm stall point. Past this point, the counterweight starts pulling in the opposite direction, actually taking energy away from the arm and projectile. This means the release should occur somewhere around the counterweight arm stall point, definitely not far after.